Good morning, students. Today we are going to discuss the topic equilibrium of concurrent forces, and it is from the chapter 5, and the chapter 5 is your laws of motion. Now this is very simple topic, equilibrium of concurrent forces. Concurrent force means the forces that act at a particular point. So here you do have O is your point, and here three forces X. One is your F1 vector upwards, and another one is your F2 vector towards left, and F3 vectors downwards diagonally. Now, if you consider F1 vector and F2 vector as the two adjacent sides of a parallelogram, then the resultant force is your F vector. It is nothing but the diagonal formed by the two adjacent sides, F1 vector and F2 vector of the parallelogram. Now, if the object which is at O is in equilibrium due to the application of these three forces, then F vector must be equal and opposite to F3 vector. So what you can write here, F1 vector plus F2 vector equal to F vector by the vector sum property. And if the system is in equilibrium, then F vector equal to minus F3 vector. Two forces are equal in magnitude but oppositely directed. That's why we have written F vector equal to minus F3 vector. So if you take F vector and F3 vector in same side, then F vector plus F3 vector equal to 0. So F vector you can write F1 vector plus F2 vector, and F3 vector is already there. So the condition for equilibrium of concurrent forces is your what? Sum of the forces should be 0. So this is very important point. Equilibrium means there is no disturbance on the object which is at O due to the application of the three forces. Now let me apply this condition, equilibrium condition, for the numerical. And the numerical is like this: a mass of 6 kg is suspended by a rope of length 2 meter from a ceiling as shown in figure. A force of 50 Newton is applied at the midpoint P of the rope. What is the angle that the rope makes with the vertical in equilibrium? Take G equal to 10 meter per second square and neglect mass of the rope. Now you see this is your diagram. Now this is your rope and a mass is suspended at its free end and one end is fixed with the support. So mass is m, so weight acts vertically downward. Now you see this length of the rope is your 2 meter as per the question is given. Now what we have done, we have applied a force of 50 Newton at the midpoint of the rope. So the diagram is like this. 50 Newton is applied, and as a result the upward rope, length of the rope gets inclined by an angle theta, and weight acts vertically downward, and the distance of the weight from the point of the application of the force is 1 meter, because we have applied force at the midpoint. So if theta be the angle made by the rope with the vertical from the support, then definitely theta is the angle with the dotted part, because it's an alternate angle. Now if T1 be the tension, then it has its component T1 cos theta and T1 sin theta, and weight acts vertically downward. So you can say that if the system is in equilibrium, then T1 sin theta balances 50 Newton and T1 cos theta balances this one, weight. So let me write T1 sin theta equal to 50 Newton and T1 cos theta equal to weight. Weight is nothing but is your mg. Mass is given is your 6 kg. So 6 into 10, so 60 Newton. So if you divide T1 sin theta by T1 cos theta, so T1 goes off, you do have 10 theta, and simplified 10 theta equal to 5 by 6, so theta equal to 10 inverse of 5 by 6. So when you see that trigonometric table, you will get theta corresponds to your 40 degree. So this is one application. Now next application we'll try to define by considering this question. The pulleys and strings shown in figure is smooth and negligible mass. We are not going to consider in the mass because it is negligible. For the system to be in equilibrium, what is the angle? Theta. Now you see this is your diagram. Pulleys and string. At the free end of the string you do have mass mm, and at the joining point you do have a mass root 2m, and theta is the angle made by the string with the vertical, so that angle is also theta. Now what we have done, we have simplified this diagram by considering this part. So tension T, theta angle, so on the vertical it has component t cos theta, and at the joining point it has a mass root 2m, so it is weight is your root 2 mg. Now if we consider the string only, then T is up and weight is down, so that is your mg. So considering these two figure from the single figure, you do have two equation. One is your 2t cos theta equal to root 2 mg if the system is in equilibrium, and you do have t equal to mg. So if you simplify this equation 1 and 2, you will get the angle theta. So 2 into mg cos theta equal to root 2 mg. So cos theta, mg goes off, cos theta equal to root 2 by 2. So you will get 1 by root 2. So 1 by root 2 is your 45 degree, cos 45 degree. So theta comes your 45 degree. So these are two applications. The diagram, once you understand, is become very easy, but if you don't understand, it's very tough. So you can apply Lemi's theorem also for equilibrium of concurrent forces, but this is not in your syllabus. That's why we are not going to discuss Lemi's theorem. So please go through this topic. It's very simple. So the condition for equilibrium is your what? Vector sum of the forces should be 0. Equilibrium means what? You are applying force, but there is no disturbance on the system. Then it is in equilibrium. And definitely for that, there must be counterbalance force, so that the applied force balances the counterbalance force. So it's a very simple, and the numerical is also, this is your NCERT numerical. Please check it in your NCERT book. And this numerical is very common in entrance. So try to go through. You will get this in any reference book if you have. So this is all about. So please check it out and find out your doubts. Next class we are going to discuss friction. Thank you.